to thank the organizers for the invitation to speak in beautiful Tel Aviv as I pour myself some water. Okay. Okay, so I'm going to talk about, it's sort of pieces of a series of recent papers. So in the last few years, there's been a lot of work on the relationship between various infrared phenomena, soft theorems, memory, and asymptotic symmetries. And one of the salient infrared phenomena that we all learn about in our first course in quantum field theory is infrared divergences. And so a natural question to ask is, what do all these symmetries have to say about this new insight into soft theorem and symmetries? What does it have to say about infrared divergences? And if anything, and the answer is quite a lot, and that's what I'll talk about now. And some of the people that I developed these ideas with are listed here, and it's in a series of papers. So the outline is I'm going to start and rederive. I'm going to begin by starting from what seems to be a completely new viewpoint, but at the end of the day, I'm going to just recover in a modern language something that has been known since the 60s, culminating in a famous paper of Fadeev and Kulish about infrared finite S matrices in QED. And that'll take much of the talk, but then I'm going to use this new way of looking things to motivate three conjectures, one having to do with QED, one having to do with non-abelian gauge theory in theories with massless gluons, and finally one having to do with black hole information. Okay, so this is a long story. I've certainly given, indeed, a whole lecture series on this, and I'm going to compress it into one slide here. And that is the story that in all abelian gauge theories, there are, in fact, something like 4 infinities of conserved charges. I'm only going to mention one here. And these conserved charges generalize the usual global charge that we talk about, the total charge. But there's one such charge for every point on the celestial sphere. So here I've drawn a picture of Minkowski space. We'll have to keep this picture in mind for the whole talk. The Penrose diagram. When we talk about the future null infinity, we'll use retarded time u. There's also advanced time v. And I'm going to label the spheres, the celestial sphere at null infinity, by z and z bar. And r is the coordinate that takes us out to null infinity. If we hold z, z bar, and u fixed, lines of varying r are null. And here I've labeled scri plus, the place where light rays go to, scri minus, where they come from. And also important in this discussion are the boundaries of scri plus and scri minus, which are 2 spheres. Scri plus minus would be important. It's the past of scri plus, and scri minus plus is the future of scri minus. They're not the same spheres, and their distinction is quite important in this discussion. So the conservation law can be phrased in many different ways, but for the purposes of this talk, I'm just going to phrase it as saying that the electric field at any point on scri plus minus is equal not to the electric field at the same angle on scri minus plus, but the antipodal one. This is something that was undoubtedly known to Maxwell, though it not usually phrased in quite that way. But it's certainly true of every reasonable scattering problem that we ever study. Now, so that sounds a little bit trivial, but it gets more non-trivial looking if you take the electric field here, use the constraints, and write it as an integral along a single null generator of scry, that is, keep the angle fixed, but write it as an integral here. And throughout this talk, for simplicity, I'm going to assume that there are only massless particles, so that nothing goes up to future time like infinity. Everything comes out here. It all has a very pretty generalization to theories with massive particles, but I won't have enough time to discuss that. So when I integrate by parts, this charge becomes a sum of two terms. One which is a so-called soft term. I use the constraint equations, which hold as strong operator equations in the quantum theory. And so it's a soft term, which is the divergence of the radiative component of the electromagnetic field, the term that is transverse to null infinity, integrated over one line. And the hard part, which will be 0 if there's no charges crossing that line. So I'm imagining that I might have massless charges which go out to null infinity. And if there is something, I can get, I just get the energy flux, the charge flux through that angle. So the integral along this angle is equal to, the conservation law is that it's equal to the integral along this angle. In fact, that's an infinite number of conservation laws. And the fact that these two things are equal after some pages of algebra is equivalent to the soft photon theorem, which is known to be an exact statement in quantum field theory. Now, it's also interesting to note that this soft charge here measures the shift if we work in a gauge where AU is 0. This is a total derivative, and this thing gives us just a shift in, we assume that the field strength vanishes here and here if the energy is finite. So we have a flat connection, AZ. It's both scry plus minus and scry plus plus. And this soft term measures the shift in the flat connection. Inequivalent vacua in QED are labeled by these flat connections. And the soft part measures how much the vacuum has changed as we go from scry plus minus to scry plus plus. And there's a similar story on scry minus. Okay, so that is the lightning review of the infinite number of charge conservation laws in QED. Now let me derive a trivial consequence of this charge conservation. Let's talk about Bhabha scattering, which has another H in it, sorry, where we take a positron and electron, we scatter them, and we ask for the amplitude to have one positron, one electron in, one positron, and one electron out. Now, we have to solve the constraints here. And here is the constraint equation written out on scry plus. So the source is here the positron and the electron going up to scry plus. And this holds for every u and z. These are coordinates on null infinity. And since this is a story, this is a picture in which there are no radiative degrees of freedom, I'm setting this to 0 when I solve the constraint equation. So the charge which comes out here sources the Coulomb field. Now, we need to set, there's nothing in the far future, we need to set it to 0. So if we solve this equation, we'll find that the Coulomb field is 0, and then it jumps and it becomes non-zero down here at scry plus minus. But unless it's completely forward scattering, if there's any non-trivial scattering, the Coulomb field that you get here from solving this constraint equation will not antipodally equal the one that you get in the bottom. So this antipodal matching condition will be violated. Therefore, this scattering process is exactly 0. So the amplitude for Bhabha scattering is exactly 0. This is well known, and it's usually derived in a somewhat more complicated way. It took many decades to sort this out carefully. And the way it would usually be stated is you start with this scattering process, and then you look at soft photons were exchanged between the external lines. And these soft photons have a pole. As their energy becomes very low, there's a pole there. And so this diagram is infrared divergent. So this diagram, this second diagram here is infinite. And so that makes it look, if you only compute this one diagram, you think that the scattering amplitude will be infinite. But actually, you should sum them all up. It was shown that they exponentiate in a nice way. And you get, instead of getting infinity, you get e to the minus infinity, which is 0. So what I'm advocating here is so that the role of infrared divergences in QED is if you try to compute something that is forbidden by the conservation laws, QFT is much cleverer than you, and it will set that amplitude to 0 by introducing infrared divergences, which just shut it down. So the moral here is that, at least as far as this kind of processes, there are no real infrared divergences in QED. They're just a penalty that we pay if we are so foolish as to try to compute something that must be 0 due to an elementary conservation law. Now, it's not very impressive just to compute 0. We can't just say things are 0. We want to actually be able to compute something. And so the problem was this Coulomb field that didn't match. So let's solve the constraint in a different way. Let's solve it not using the Coulomb field, but using the radiative modes. And it's not too hard to solve this equation. So we can solve this constraint equation by dressing the charge with a cloud of radiative photons. And here's the solution. Notice that this A here has a theta function. And if we were to go into momentum space, that would mean that it has a pole as omega goes to 0, because the Fourier transform of a step function is a pole. And notice also that this A has the property that because of this step function, that it's going to be flat. This is pure gauge except at u equals u0. It's a flat connection except at u equals u0, where there's a radiative shock wave that's coming out with the electron. There is a shift in the flat connection. So when we do this, we're talking about a situation in which we're making a transition from one vacuum to an inequivalent second vacuum, both with flat connections. Here I just solved a classical problem, but we can promote this to a quantum state by just dressing it like this. This is now a field operator. And we find that if we act on this with the constraint equations, everything now being an operator, that this is annihilated by the constraint equations. So this would be a dressed state of a positron or an electron, depending on the sign here, in which there is no Coulomb field. We've instead shielded it with radiative modes. Now, of course, you can't shield the 0 mode. You can shield everything but the 0 mode. And And so, but here I'm talking about Bhabha scattering, where the net charge of the whole thing is 0. So I can find a radiative dressing which sets the Coulomb field to 0 outside the dressing. So this trivially, since there's no Coulomb field, if I scatter these dressed states, I'll obey the conservation law in a trivial, all the infinitive conservation law in a trivial way. Now, the beautiful thing is that the scattering of these dressed states is completely infrared finite. This is something that was shown by Fadeev and Coolidge, proved, some people say, almost 50 years ago. And what happens is that they did it all with diagrams. What happens is that these exchange diagrams, every exchange diagram between a pair of two external legs is canceled by a similar diagram where you exchange a photon between a leg and the soft cloud, this radiative cloud that surrounds the charged particle. Now, one thing I'd like to clarify, if you look at the old papers of Fadeev and Coolidge, it sounds as if they don't say anything wrong, but one gets the impression that what happens is that you have a charged particle going off to infinity surrounded by some mysterious cloud of photons. But of course that doesn't happen. Photons go to null infinity, and massive particles go to time-like infinity. So this cloud of photon doesn't stick with the particle. It disperses out to null infinity, and its goal is not to, its real goal in life is to satisfy the conservation law. It's a long distance effect, and indeed the Fadeev-Coolidge clouds are highly ambiguous. It's only thing that matters about them is, as they emphasize, is that they have the right pole structure. They don't have to be near the particle. They just have to shield the Coulomb field so that the conservation law is satisfied. Okay, so that is my reinterpretation of some beautiful work that was done by quantum field theorists Chung, Kibble, Fadeev, and Coolidge in the 60s and 70s. But now I'm going to use this physical picture to make three conjectures. So the first one has to do with QED. So there's a big problem with Fadeev-Coolidge states are not very physical. At the LHC, when we throw in protons, we don't follow them up by a cloud of soft photons that shields the variation in the Coulomb field. We just throw in protons typically without adding any radiation. So it's not satisfactory to cancel infrared divergences only in states that consist of charged particles without clouds. We should be able to just throw in some particles and see what comes out, and it should be infrared finite. In fact, so the first conjecture is that this is possible. As I said, it doesn't really matter where these charged clouds are, and the conjecture is that you can move one of the charged clouds from the in state to the out state. One way of thinking about this is we could take an operator which creates that cloud with a negative sign, and because there are no poles as photons get near charged particle plus cloud, such a cloud would not interact. It would just cancel the incoming cloud and replace it with an outgoing cloud. It's like the difference between solving the scattering problem with the retarded potential rather than the advanced potential. What Fadeev and Coolidge effectively did is they used the advanced potential to find the radiative modes for all incoming things and the retarded ones for the outgoing things. So the conjecture is that if you just use the retarded one, which is the more physical one, for ingoing and outgoing, that the infrared divergences will cancel. And you can check that at leading order, I haven't done a careful analysis to all loops, that this cancellation still occurs when you move this cloud from the in state to the out state. And that is, this exchange diagram is canceled, the infrared divergence is canceled by the exchange between this outgoing positron and the cloud that was once there but now has been moved up to there. Okay, now I'm going to make a similar conjecture even for non-abelian gauge theory. So in QED, it seems that the only role of infrared divergences is to set things to zero which violate conservation laws. And so it's natural to conjecture that even in non-abelian gauge theory, where the structure of the infrared divergences is a lot more complicated, that as long as we satisfy all the conservation law, there will be no infrared divergences. Finally, let me get to gravity, which I just had a paper on this in the last week. So here we have a picture of a black hole formed by gravitational collapse of some classical matter. Eventually, it evaporates and disappears due to the Hawking evaporation. Now, it evaporates at the Hawking temperature, and a typical outgoing state will consist of black body radiation with an energy distribution or a distribution of quanta, which goes like omega squared at small energies. And so we can think of all of the Hawking quanta as hard quanta because their densities goes to zero with omega. There is no pole. And so Hawking conjectured in 1975 that a generic in-state will evolve into a mixed out-state where this is some, a thermal out-state, where this is all states in some thermal radiation ensemble. Now, Page came along 5 years later, and he made an alternate proposal. And his proposal was that the evolution is unitary, and it goes instead to C alpha times some collection of some H alphas, where these C alphas were some typical state in the thermal ensemble that Hawking computed. And moreover, he said that purity should be restored by correlations in this picture between the late time hard quanta and the early time hard quanta, with the deviation from thermality beginning halfway through the evaporation process at the Page time. Now, this is impossible because each one of these processes, if we make a black hole with no incoming charges, each one of these violates a conservation law. It is impossible to make a bunch of hard quanta without also there being a bunch of soft quanta whose distributions have poles at omega equals zero. So we could understand that in terms of the analog, the gravitational analog of the conservation law I just discussed, super translation charge conservation. Every one of these states will violate that conservation law, or we could draw the exchange, we could do it the hard way, we could draw the graviton exchange diagrams between the outgoing hard Hawking quanta, correct the Hawking calculation, exponentiate those diagrams, and show that every one of the Hawking amplitudes is zero because of resummed infrared divergences. So I want to replace it with an alternate conjecture, which is that the in-state goes to a unitary out-state, but the out-states are the hard states dressed as they must be by the conservation law by soft quanta. And then the second part of the conjecture is that the soft quanta know what the hard state is. They're in one-to-one correspondence with the hard state. And so if we trace over the soft quanta, in other words, if we do the measurements with a detector that has some infrared cutoff, that the result is exactly the Hawking density matrix. And so here the purity is restored not as Page conjectured between the late time and the early time hard quanta, but between the hard quanta, which are completely uncorrelated with one another, and the soft quanta, which must appear due to the conservation law. Now, could it be true that the soft state knows what the hard state is? And I don't know if this is true in general. What I argue in the paper is that if we consider a theory in which the only stable particle is a graviton, that it is true. And here we have, again, this conservation law, and we have to work, which has a soft piece and a hard piece. We have to work in a basis which diagonalizes the hard piece. So let's choose that basis. And if we take an incoming state in which all the supertranslation charges vanish, then the soft part must equal the hard part. And so the question is whether this uniquely determines the outgoing hard state. And the answer is almost yes. It's not quite yes because we could have two gravitons. This measures the angle that the graviton comes out at. This is the energy of the graviton. We could have two gravitons with half the energy going to exactly the same angle, and that would give the same supertranslation charge. So there's a little degeneracy there, but the probability of that is 0, of two exactly collinear hard particles is 0 in the Hawking distribution, and so that doesn't affect the discussion. Now, this doesn't see the graviton spin, but there's a second conserved quantity, the superrotation charge, which does see, I'm almost finished, which does see the graviton spin. And if we use that, we find that every soft state has a different eigenvalue, and therefore they must all be orthogonal, and we can choose a normalization in which S alpha beta is delta alpha beta. And so tracing over the soft quanta will fully decohere all the hard ones. And there was a very interesting paper last week by these authors who used completely different methods, who also showed it just in ordinary scattering processes, they weren't really specializing to black holes, that tracing over soft quanta typically completely decoheres a scattering process. Now, I want to stress here that I haven't solved the information problem. I haven't said why we should have a pure state of this type. Neither did Page give any proposal for how you compute the CMs. I've just given a different procedure which is in harmony with recent work on soft particles in black holes and quantum field theory, that a different mechanism by which the quantum purity might be restored. And in particular, I haven't said anything about how one would hope to compute these phases. So that's it. So the conclusion is that there's a lot more to be understood about the soft structure, not just the high energy structure, but even the soft structure of the world around us. Thank you.
Thank you very much for this very inspiring talk. Are there questions? Yes.
In QED, once you've dressed your electrons the way you did, you get a finite scattering amplitude. Does that obey the usual kind of unitarity relation?
Sorry, I couldn't. You're maybe holding the microphone too close, or maybe don't hold the microphone, Shiraz. You don't need a microphone.
Do your finite scattering amplitudes in QED
Well, QED is unitary. The question of whether the Faddeev-Coolidge basis is a complete and unitary basis is, I don't think it's been fully addressed, but I would say it's incomplete because it doesn't allow you just E plus E minus. At the LHC, we don't scatter Faddeev-Coolidge states. Now, whether or not you want to say it's unitary, you have to, slightly subtle question because there's superselection sectors associated with the conserved charges. So is the scattering of all states with charge 5, is that unitary? It might be that it's unitary but doesn't cluster properly.
But suppose I just take the functions S of P, S star of P, and integrate over the internal P's. Do the usual thing we try to do to check unitarity. Would it obey S minus S star? Just at loop level.
I think people have argued that.
That it does.
Yeah.
Other questions?
It's often said that in quantum gravity and flat space, the S matrix is the only well-defined observable. But I find this confusing if quantum gravity includes some subsector where there's, say, a conformal field theory coupled to gravity. Does your approach sort of shed light on how to understand that situation?
I would still say the S matrix is the only observable. It doesn't help that much to have a conformal field theory. Once you couple to gravity, it's not conformal anymore.
So you're saying there isn't a well-defined S matrix in that?
Well, you mean, because of the infrared problems in conformal field theory itself. Yeah. Well, I guess I already made a lot of conjectures. I don't know what to say about that. I said that infrared finite. The scattering amplitudes are finite. So yeah.
Another question. There are a lot of questions there.
I didn't understand why the resolution by page is mutually exclusive with the resolution that you mentioned. It could be that the hard quanta are entangled with the soft quanta, and it could also be that the late dressed quanta are entangled with the early dressed quanta. So I didn't understand why these two setups are mutually exclusive, particularly because at least in some examples you might expect the latter scenario I described to hold.
Well, that would be a fourth conjecture, that the late dressed quanta are. I don't think that. I didn't. In quantum gravity, I'm not sure that entanglement entropy on scry in flat space is across a cut. I'm not sure that that is well defined. There are issues with dividing the Hilbert space of the soft gravitons, and there's also it has to transform properly under supertranslations. And I wrote a paper with Anna Reclario and Dan Kopetz, just pointing out that there are a lot of subtleties in that. So I was trying to keep myself. So I didn't mention that because I don't know what it means to say late and early, but it could be that something like that happens. Though I don't know why it needs to happen.
Sorry, I have to stop the discussion. I'm very sorry for all the questions that should come, but we have to be in time because of the social activities. So let's thank Andy again.